Hello everyone, welcome. What we have discussed in the last class is we derived the slope deflection equations and then also discuss how that slope deflection equation for we need to derive, we need to obtain that equation for each segment separately and then combine them to get the final system of equation and solve those system of equation to get the unknown displacements. Once we know the unknown displacements, again we can apply them to slope deflection equation to get the internal forces. What we will be doing now today and then next two classes is we will just demonstrate the concept through several examples. The examples that we consider today is the example of a continuous beam. This is the example that we will be considering today. Okay. So, it is the idea is to demonstrate the concept, is the numerical demonstration of the concept. We could have taken more complicated structure with the number of spans and more, but the essence of the concept will remain same irrespective of the problem, right. So, the idea is as before doing any example, as I always said, the idea is not to particularly solve an example in this class. The idea is through that example we demonstrate the application of the concept. Okay, great. So, we need to find out what is the internal forces in this structure. This is a statically indeterminate structure. So, now let us draw the structure. The problem is like this is a so this is a roller support and this is hinge support, this is fixed support, this is A, this is B, this is C, and it is subjected to an internal in uniformly distributed load, which is 3 kilonewton per meter, and then at the mid span the concentrated load, which is 10 kilonewton. Okay. This length is 5 meter, this is 2 meter and 3 meter. Okay. This is the problem. Great. Now, the step 1, first step is again we take the member, we consider the member AB and BC separately and then and apply the slope deflection equation for member AB and member BC separately and then combine them through equilibrium equations. Okay. Now, so step 1 is fixed end moment, we need to determine the fixed end moment for all the segments. So, first consider for member AB is M, AB fixed end moment at A in segment AB is equal to, you see this becomes a fixed, this entire structure is subjected to uniformly distributed load, and recall for this kind of for a fixed beam subjected to uniformly distributed load, we obtain this fixed end moments becomes the, if it is Q L square by 12. Okay. And the sign of this is Q L square by 12. Okay. This is this and this is this. Okay. This is how the moment, this is a hogging moment. Okay. Now, in this direction it is anti-clockwise and in here it is clockwise, and similarly that we have done, and if you take any book, so this is already given. So, this fixed end become at A, it is anti-clockwise. So, this is minus QL square by 2, Q is equal to 3 into L square 5 square divided by 12, this kilonewton meter, which is equal to minus 6.25 kilonewton meter. Okay. Now, similarly we can calculate M F BA, this will also be WL square by 12, but the positive sign because it is clockwise. So, this become 6.25 kilonewton meter. Okay. So, this is MABF. So, we have this is the fixed end moment and this is the fixed end moment, right. Now, we need to find out the fixed end moment for this is for span AB, this is for span AB, this is for span AB. So, similarly, we can do it for span BA. So, span BA will be span BC will be fixed end moment at BC, MBC fixed end moment, that is fixed end moment at B due to externally applied load at any arbitrary point. This becomes P into A B square divided by L square, that you can find out from any book. So, this becomes 10 into 2 into 3 square divided by L is 5 square, L is 5 square. Again this is negative. So, if this is the structure and this is arbitrary load, we have a moment in this direction and moment in this direction. Okay. And so, it is at this point it is anti-clockwise, at this point it is clockwise. So, that is why it is negative, and this become minus 7.2 kilonewton meter. Okay. And similarly, we have MCB F is equal to 7.2 kilonewton meter. This will be not 7.2. If you apply the same formula, this will get 4.8 kilonewton meter. Okay. Now, I leave it to you to check the formula here. You can get this. So, this is for span BC. Okay. Now, we have the expression for span AB and span BC. This is the fixed end moment. This was our first step. Okay. Now, this was the first step. Okay. Now, step 2. Step 2 is we need to apply slope deflection equation. Okay. So, what is step 2? Now, first we apply slope deflection equation for member AB and then slope deflection equation for member BC. Now, let us first for AB. Now, what is, if you recall, the slope deflection equation, final slope deflection equation was MAB is equal to MABF, that is fixed end moment, plus the stiffness into corresponding rotation. This becomes 2 EI by LAB into 2 theta A plus theta B minus 3 delta by L A B. Okay. This is the slope deflection equation. Okay. If you the equation that we derived in the previous class, if you simplify this you get this. Now, for this problem delta is equal to 0, delta is equal to 0, there is no settlement. So, this will go. Okay. LAB is the length of AB, and EI is the flexural rigidity of AB. In this example, it is assumed that flexural rigidity is constant for both the span, and ABF is the fixed end moment at A. So, if we apply that, so what we get M AB is equal to a fixed end moment is minus 6.25 plus 2 EI by 2 EI by 5 into theta B. Now, another important thing is theta A is also 0 here because it is fixed end. So, fixed end your rotation at A is equal to 0. So, straight away we can write theta A is equal to 0 and delta is equal to 0. So, only we are left with theta B. Okay. So, this is equation 1. This is equation 1. Okay. See, this is the moment slope deflection equation for member AB. Now, similarly, we can have MBA. MBA will be again same thing, fixed end moment at B plus okay, let us write it. So, MBAF, fixed end moment at BF plus 2EI by LAB into theta A plus 2 theta B. Delta I am not writing here because delta is 0. Okay. Now, MBA is equal to MBF is 6.25 plus again theta A is equal to 0, it is fixed end. So, this becomes 4 EI by 5, this is theta B. So, this is equation number 2. Okay. So, this is the slope deflection equation for member AB, and this is at A and this is at BA. Okay. Now, similar exercise we have to do it for other member, means member BC. Let us do that. Now, for BC, and what is the expression? We have MBC will be MBC then fixed end moment plus 2 EI by LBC into 2 theta B plus theta C. You can write the general expression delta, but delta is 0. So, not written explicitly. So, now MBC is equal to, we have already obtained, this is minus 7.2. So, MBC becomes minus 7.2 plus 2 EI by 5 2 theta B plus theta C. So, this become equation number 3. Okay. This become equation number 3. Okay. Now, let us do it for MCB. MCB is MCBF plus 2 EI by LBC into theta B plus 2 theta C. You can do it in matrix form as well. This becomes MCB is equal to, this is 4.8 plus 2 EI, then this is 5, then theta B plus 2 theta C. Okay. So, this is equation 4. Okay. So, we have obtained what is MAB, MBA, MBC and MCB. This was so we have applied slope deflection equation for all segment. Now, next part is application of equilibrium equation. What we do is, next part, now step 3. Step 3 is equilibrium condition. Now, equilibrium condition means we need to apply equilibrium at B, and similarly we need to apply equilibrium at C. What is equilibrium at B? Equilibrium at B will be at B is MBA plus MBC is equal to 0. Okay. Now, we have already obtained the expression for MBA and MBC, and if we substitute that here, we will get MBA was 6.25 plus 0.8 EI theta b, and MBC was minus 7.2 plus 0.4 EI 2 theta b plus theta c, that is equal to 0. Okay. So, this is equilibrium condition at B. Now, similarly, we can have equilibrium condition at C, and what is the equilibrium condition at C? Equilibrium condition at C will be MCB is equal to 0, because it is only moment you have is MCB, and then MCB will be 0 because it is a simply supported end. Okay. Now, MCB is equal to 0, we have obtained for expression for MCB, and if we substitute that here, then it becomes 0.4 EI theta b plus 0.8 EI theta c, that is equal to plus 4.8 is equal to 0. 0.4 EI theta b plus 0.8 EI theta c plus 4.8 is equal to 0. So, this is one equation and this is another equation. Okay. Now, this how many unknowns we have here? We have two unknown, rotation at B and rotation at C. So, we have two equation, this equation and this equation. Okay. Now, this equation is applying the equilibrium at joint B, and this equation is applying equilibrium at joint C. So, we have two equation and two unknown theta b and theta c. If we solve them, then we get the expression, expression for theta b and theta c as this. We get theta b is equal to 2.393 by EI, and theta c is equal to minus 7.196 by EI. This is the theta b and theta c. Okay. Now, once we have theta b and theta c, what we need to do next is we need to just substitute these values of theta b and theta c in this x. See, this is the slope deflection equation for AB. Now, in this expression, if we substitute the value of theta b, we will get what is the value of MB, and in this expression, if we substitute the value of theta b, we will get expression for MBA, and similarly this is the slope deflection equation for BC, and if we substitute theta b and theta c here, we get BC, and if you substitute theta b and theta c here, we get CB. You should get CB is equal to 0, because the moment MCB is equal to 0, because moment at CB is equal to 0 here. Okay. So, now if we do that, then the final results that you have is MAB is equal to minus 5.29 kilonewton meter, and then MBA is equal to 8.16 kilonewton meter, and MBC is minus 8.16 kilonewton meter, and MCB is equal to 0. So, that is the final internal forces you have. Okay. Now, if we have to draw the bending moment diagram, how we can draw the bending moment diagram? The actual structure was something like this. This end was fixed, this is roller, and this is hinge support. Here you have uniformly distributed load and a concentrated load like this. Okay. Now, let us draw the bending moment diagram. Now, bending moment diagram will be, first is you draw the bending moment diagram for these external load individually for all segments, and then the bending moment for this. Okay. bending moment for this. Now, if you do that, then your external load bending moment diagram will be something like this. The external load bending moment will be something like this, and then something like this. This is the bending moment for external load, and then finally, you have now one thing, please make sure these values, that what you get, the sign that you get, that sign gives you whether the moment is clockwise or anti-clockwise, right. This sign will not tell you whether the moment is sagging moment or hogging moment, but when we draw the bending moment diagram, we use the convention, the sagging moment and hogging moment. Let us see whether these moments are, how these moments look like. See, MAB is minus 5.29, minus 5.29 means it is anti-clockwise. Anti-clockwise means this moment is in this direction. Okay, this is MAB, and then MBA is 8.16. It is positive. It is positive means it is clockwise in this direction, and MBC is minus 8.16, which is negative. Negative means anti-clockwise direction, and MCB is 0 here. Another important thing to be noticed, you see MBA plus MBC is equal to 0 here, and that is very obvious because at this point there is no external loading. So, the internal forces, they should balance each other, cancel each other, right. Now, when you draw the bending moment diagram, we check whether the moment is hogging moment or sagging moment. Because of this external load, the moments will be sagging moment, because this external load will cause sagging in this segment. That is why it is drawn on the upper side. Okay, always at least this is the convention that we have been following in this course, that we draw the bending moment in the compression side. Okay, now this is positive bending moment. Okay, now next is, on top of this, these are all negative bending moment. So, this value is 5.29, this value is 5.29, and this value is 8.16, and then this become this. Okay. So, this is positive and this is negative. So, some part will cancel each other. So, your bending moment will be only this part. Only this part will be your bending moment. Only this part will be your bending moment, and let us write the values. So, this is 5.29 and this is 8.16, and this value is 12.5, and this is at the max, this value is 9.375. Another way of drawing bending moment that we also discussed, that you draw this bending moment like this. The first you draw the negative bending moment, which is like this, and from the negative bending moment we can draw the positive one. Okay, something like this, something like this, and then from that we can get something like this. Okay. So, then in that case this becomes your bending moment diagram. We check this bending moment diagram, do not take it for granted. Okay. So, this becomes your bending moment diagram. Now, you look at so this is your positive, all this positive, and this becomes negative, this is also negative. Okay. So, let us see. So, this part is negative, we have a negative part which is below the this is our beam, negative part, then this part is this part, and this entire this part is this part, and then this part is this part. Okay. So, this can be your bending moment diagram, or this can be your bending moment diagram. The advantage and disadvantages, advantage here is the drawing is become easier, and but the advantage here is you really do not have to say which one is negative, which one is positive. Just by looking at the bending moment diagram, you can say that which part is sagging and which part is hogging, or in other way, which part is under tension, which part is under compression. Okay. So, this is a demonstration of slope deflection method for a beam, which is relatively simpler. As I said, the idea was not to analyze any particular structure. Idea has been to demonstrate the concept of slope deflection method. What we will do next is we will again demonstrate the concept through some examples, through some frame examples. Okay, we stop here today. See you in the next class. Thank you.